Assalamualaikum and greetings everyone. We are still on surface integral of a vector field where we use it to find flux of vector field. Now I'm gonna show you an example. Let's look at example A. Here we are asked to find flux of vector field F across the surface sigma if F is this and sigma is the portion of the surface that equals 1 minus x squared minus y squared above the xy plane oriented by upward normals. Okay, so here we have our vector field F and also surface sigma. Now let's sketch our surface sigma. It's a paraboloid, but if you don't remember how to sketch this, you can always look at the view from the front, from the side, and from above. Let's say Z. The view from the front is when x is 0. So when x is 0, we get Z is 1 minus y squared, which is a parabola open downwards, shift 1 units up, okay, and the intersection is 1 and negative 1. And when a y is 0, we get a parabola as well. Oops, 1 minus x squared. So this would be a view from the side. We have x and z. And again, we have a parabola open downwards, intersect the x-axis at 1 and negative 1. And when z is 0, we have 0 is 1 minus x squared minus y squared. Rearrange the equation, then we can see that this is an equation of a circle of radius 1 centering at 0, 0. Okay, now when we put everything together, let's say that's a 1, a 1, and a 1. We don't need to sketch for below the xy plane because it says above the xy plane, so we just draw only up till here. So this is a 1, this is negative 1, that's a 1, and here we have a 1. So this is a paraboloid. I'm gonna erase this bit because we want flux of F. We want to find flux of F. Alright, so flux of F, as you recall, is given as flux of F is equal to F dot unit normal vector ds integrate over surface sigma. What we're going to do is we're going to project this onto a plane. So unit normal vector will be replaced by normal vector dA over region R, where R is the projection of surface sigma. Okay, now since our surface is given as z as a function of x and y, what we're going to do is we're going to project our surface sigma onto the xy plane. So if we project that onto the xy plane, what we get is a circle of radius 1. So what we have is a circle of radius 1. Okay, now we need to find the normal vector. Okay, so remember from before, our normal vector is either the gradient of phi or negative gradient of del phi or negative del phi. We have to check for the z component. Okay, alright, so here our surface is given as z as a function of x and y, so we need to check for the k component, the z component. And here you can see that it is facing the positive z-axis. So what we want is we want our k, the x component, the z component, we want it to be positive. Okay, now rearrange our surface sigma into a function of x, y, and z. So that would be z minus 1 plus x squared plus y squared. Now take the gradient of phi, differentiate phi with respect to x, we get 2x. With respect to y, we get 2y. With respect to z, we get 1. And we want our z component to be positive. It is already positive. Then we know that this is our normal vector. Okay, so normal vector is equal to gradient of phi or del phi. Okay, now we need to dot f with n. Okay, oops. Now we need to dot f and n. Okay, let me erase this. Okay, so we have our vector field f. We need to dot that with normal vector. So f is xi plus yj plus zk. And the normal vector, we already evaluate our normal vector, which is 2xi plus 2yj plus 1k. So when we dot this, we get 2x squared plus y component with y component, we have 2y squared, and then we have plus z. Okay, so that is f dot n. Okay, writing it here. So that is equal to 2x squared plus 2y squared plus z, and we're going to integrate this over region R, which is on the xy plane. Okay, now you can see that z there, we cannot have z anymore because the integration is over a region R, which is on the xy plane. So we would have all the terms should be in terms of x and y. So we're going to change, we're going to replace this z here with our surface. Remember, z is 1 minus x squared minus y squared. So we're going to replace that z with the surface. So that would be 2x squared plus 2y squared, and z is 1 minus x squared minus y squared, and everything here we need to integrate this over region R, which is on the xy plane. Okay, now simplify our integrand. We have 2x squared minus x squared, so we have 1x squared, and here we have 2y squared minus y squared. Again, we have 1y squared, and we have plus 1 dA integrate over region R, which is on the xy plane. Okay, so now we back to double integral. Now let's look at our region R, which is on the xy plane. It is a circle. Okay, let me sketch that circle. So we have a circle, and the radius of the circle is 1 on the xy plane. The radius is 1. Oopsie. Here. Hang on. Alright, so the radius is 1. Okay, that's a 1, I guess. So we have a 1, a 1, negative 1, negative 1. So this is our region. So now we're back to double integral. Okay, so referring to our region R here, we can see we have two choices, either Cartesian or polar. But since our region is a circle, we're going to use polar. So using polar, x squared plus y squared will be replaced by r squared. 1 is still 1. Excuse me. And dA is r, dr, d theta. Okay, so now we're back to polar coordinates. Now to get the limits for r and theta, just refer to our region. Draw a straight line from the origin across our region. You can see that it is the region starts from the origin and then it stops on the blue circle. So r is from 0 to 1 because the blue circle is r equals 1. And the limits for theta, we have a whole circle here, so theta is going to be from 0 to 2 pi. Okay, now let's evaluate. Okay, integrate with respect to r. We have here r cubed. That will give us r to the power over 4. And here we have r. Integrate r, we get r squared over 2. And then replace r with upper and lower limits, which are 0 and 1. So here we have 1 over 4 plus 1 over 2. 1 over 4 plus 1 over 2 is 3 over 4. Okay, so we have 3 over 4. Now integrate d theta from 0 to 2 pi. So we have 3 over 4 theta, 0 to 2 pi. So from here we get 3 pi over 2. So that is the flux of F. Okay, thank you.